What's up geeks, and welcome to the channel. In this video, we're diving into Java generics. Why do we use them? When do we use them? And how can they make our code clean, flexible, and reusable? As always, we're going practical. Imagine we're building an application and we write a method to sort a bunch of numbers. The method takes a list of integers as input and returns a sorted list. Simple, right? But then we realize another part of our app needs to sort strings, not numbers. At this point, we've got two choices: either duplicate the sorting method and tweak it to handle strings instead of numbers, or make the original method generic so it can handle any type, numbers, strings, or even custom objects. Obviously, we go with the second one, and that's where Java generics come in. Now, here's the thing, we've been using generics already without even thinking about it. Remember how we used a list of integers or list of strings? The list class is a generic class. It takes a type parameter so it can hold whatever type we choose. So, to make our sorting method generic, we need to make the class containing it generic too, just like the list class. We do this by introducing a type parameter, usually t, which we can then use throughout the class, including in our sort method. And with that, our method now works for integers, strings, doubles, and whatever we want. If we want to sort strings, for example, we just instantiate our class with t set to string. And while t is the convention for type, we'll often see k for key and v for value when dealing with maps or key-value pairs. We can also use multiple typed parameters if needed. Now, maybe you're thinking, do I really have to make the entire class generic just to have a generic method? Good news, we don't. That's where wildcards come in. A wildcard in Java is represented by a question mark, which stands for an unknown type. We can use it to make a single method generic without affecting the whole class. The method we see can now accept lists of integers, strings, and more. And that works mostly, but here's the catch. It can also accept a list of mixed types like integers and strings together. That compiles fine, but when we run it, expect an exception. To fix that, we should always specify the list's type when creating it. Avoid raw types like just list. Always write list of strings, list of integers, etc. That's the best practice in general, not just here. Another way to fix it is using bounded wildcards. If our method is meant only for sorting numbers, like integer, double, float, we can limit the wildcard by adding extends number. This ensures only numeric types are accepted at compile time, preventing unwanted runtime errors. Just like we can bound wildcards, we can also bound generics. We can even use multiple bounds on both, like t extends number and comparable. Here, t must be both a number and comparable. If it fails to meet either condition, we get a compile time error. Quick side note before moving on. Ever wonder why we can't use primitive types such as the integer with generics like list of ints? That's because generics work at compile time, and during compilation the type parameter t gets erased and replaced with the object class. And since int or double don't extend the object class, we can't use primitives in generics. Okay, now that we know what generics and wildcards are, let's tackle the difference between plain generic unbounded wildcards, upper bounded wildcards, and lower bounded wildcards. Let's start simple. Suppose we have a doStuff method that takes an array of objects. Can we pass it an array of strings? Yes, because an array of strings is a subtype of an array of objects. Now, what if we change the parameter to a list of objects and try to pass it a list of strings? Nope, won't compile. That's because generics in Java are invariant. Okay, before we tackle what this means, notice that the error we got is actually a good thing. Imagine we decided to store integers in the array of strings we passed to the method that takes in an array of objects. What would have happened? Our code would have compiled with no errors, but we would have got a runtime exception. So, making collections and generics invariant shifted our errors and exceptions from runtime to compile time, and that is one hell of a benefit. So, what does invariance mean? And if collections are invariant, what about arrays? Well, there are three main terms we should be aware of: covariance, contravariance, and invariance. Covariance means that if we have a type t, only type t and subtypes of t are allowed in this context. In Java, this is represented by the upper bounded wildcard, and by nature, arrays in Java are covariant. On the other hand, contravariance means that if we have a type t, only type t and supertypes of t are allowed in this context, and this is represented by the lower bounded wildcard in Java. Finally, invariance means that if we have a type t, only type t is allowed in this context. No supertypes or subtypes of t are allowed. To further understand the difference, let's take practical examples. Suppose that we have a method that calculates the sum of numbers in a collection. Now, as we previously established, collections are invariant, so if we try to pass into the method a list of integers or doubles, our code will not compile. In this case, the extends wildcard is the answer. As you see, the compiler is now happy and allows us to pass a collection of a subtype of number. However, there is something we need to keep in mind while using this upper bounded wildcard. We can't add elements to the collection declared with the extends wildcard. If we try to add an element, the compiler will throw an error. Adding a double to an integer-only collection, for example, is not allowed. The only acceptable addition is null as it applies to all types. So, we made use of the extends wildcard in this example because we were retrieving the elements from the collection to sum them, and we weren't trying to alter the collection by adding elements to it. Okay, now suppose we have the following method that adds the integer numbers from 1 to 5 into a given collection. Additionally, we have a list of numbers to which we want to add these integers. The method we wrote accepts a collection of integers, and hence it's illegal to pass a list of numbers to it. And here, the extends wildcard cannot be used, because number is a supertype of integer and not a subtype. In this case, the super wildcard is the solution. After updating the signature of our method, it is now legal to pass to it our list of numbers. The compiler is happy and leads to the desired output. With the super wildcard, we can also pass a list of objects. However, there is a catch. If we wanted to retrieve the sum of these elements declared with the super wildcard, we wouldn't be able to do that. The compiler can't execute the sum operation on a list storing integers and strings at the same time. So, in this example, we made use of the super wildcard because we needed to add elements into the collection, we needed to alter our list, and we weren't trying to retrieve these elements from the list. The examples we gave and my emphasis on when we needed to add or retrieve elements from the bounded collection was to lead to a mnemonic for wildcard usage. And it goes by PECS. Producer extends, consumer super. So, if t is a producer, which means when we are passing in a parameter from which we are producing t's, we want to get t's out of this parameter, then we should use the type $extends t. Whereas, if t is a consumer, which means when we are passing in a parameter into which we want to put the t's, the thing consumes elements of type t, then we should use the type $super t. In short, use extends to only get values out of a structure, use super to only put values into a structure, and don't use a wildcard to both get and put. Now, what I just said can be represented by the small table we see. So, if we are producing and consuming t's, it means that the object we are dealing with is invariant in t. We can only work with t's, not its subtype nor its supertypes. If we are only producing t's, it means that the object we are dealing with is covariant in t, and we should make use of $extends t. If we are only consuming t's, it means that the object we are dealing with is contravariant in t, and we should make use of $super t. Finally, if we aren't producing nor consuming t's, it means that the object we are dealing with is independent of t. We should make use of unbounded wildcards. Okay, the last thing I want to talk about are return types. Notice that in all of the examples we gave, bounded wildcards were only being used as method parameters, never as method outputs. Why is that? Well, why do we use wildcards? We use them to make our APIs and methods more flexible. Our methods should just work. Clients making use of these methods or a particular library shouldn't have to think about wildcards or about passing specific parameter type. But what happens if we return wildcards? The people making use of our API will have to create a variable of the wildcard type to store in the return value, and this will strip the clients of the flexibility we previously guaranteed, as we just made it more difficult to use. Let us know in the comments below if you'd like to see more videos about generics and wildcards in Java. And that's it for this video. I hope it was helpful. If you learned something new today, hitting the like button and subscribing really helps the channel out. Thanks for watching, take care, and I'll see you in the next one.